Characteristic features of synchronous motor. Basically, it runs either at synchronous speed or not at all. It is not self-starting. It has to be run up to synchronous speed by some means. It is capable of being operated under a wide range of power factors. So these are the main characteristic features of synchronous motor. The first one is about it runs on synchronous speed only. It is not self-starting. It is capable of being operated under a wide range of power factors. Now let's discuss about the constructional detail of synchronous motor. The important points of construction of synchronous motor are stator, stator winding, rotor winding, exciter, slip rings and brushes. Let's discuss one by one. First one is stator. It is a stationary part made of silicon steel stamping having slots on inner periphery. Stator winding. It is star or delta connected super enabled copper winding inserted in stator slot. Rotor. Rotor is a cylindrical part having poles on surface and it also made of silicon steel stamping. There are basically two types of rotor. One is salient pole type and the other one is smooth cylindrical shape rotor. Now rotor windings. Enamel copper windings is put on the poles and excited by DC supply received from exciter. An exciter is a small capacity DC generator generally mounted on the same shaft of the rotor, and when moving generates DC supply to be fed to the rotor winding. Means the exciter is used to excite the rotor of the motor. Now next point is slip rings. Slip rings and brushes. There are two slip rings made of phosphor bronze. The material used for slip ring is phosphor bronze and they are heated on two carbon brushes are kept touching with the slip. Now this is the construction diagram of synchronous motor. Here you can see the exciter which is attached to two slip rings and this hashing part is nothing but two brushes which are attached to slip ring and they are mounted on the same shaft of the motor. So this is the shaft of the motor and here you can see the synchronous motor. This inner part is the rotor which is having N pole, S pole, N pole, S pole. And these are the stator winding and this round part is the stator of the motor. So this is all about constructional diagram of synchronous motor. Now why the synchronous motor is not self-starting? Basically, you can see here three diagrams with a torque in an anti-clockwise direction. There is one torque in clockwise direction and by this diagram you can learn about the working of synchronous motor. When three-phase stator winding is supplied by the three-phase supply, then the magnetic flux of constant magnitude, but it is of the rotating magnetic flux at a synchronous speed is produced. And DC voltage from exciter is supplied through brushes and slip rings to the rotor. Thus, the rotor poles are formed as N and S. Suppose the stator pole are at that instant situated at a point A and B. The two similar poles, N of the rotor and NS of the stator as well as the S and the SS will repel each other and rotor tends to rotate in the anti-clockwise direction as shown in the above figure. But after a half period, stator poles having rotated around interchange their position. NS attracts S and SS attracts N. Hence, the rotor tends to rotate clockwise as shown in figure. Now the rotor is not subjected to unidirectional torque owing to large inertia because there are two forces. One is acting on the clockwise and there is After the half period, there is another force which is acting in opposite direction. So due to the inertia, the rotor remains stands. Rotor cannot respond to such quickly reversing torque. With the result, it remains stationary. Now, how the motor can be started? Now here the diagram you can see how exactly the motor is started. If the rotor poles also shift their position along with the stator poles, then there will be a unidirectional torque. Hence, by some mechanical force, rotor is rotated, then there is a magnetic locking between stator and rotor pole. So this is Ns is the stator pole and S is the rotor pole. So there will be a magnetic locking between them, between stator and rotor pole. And even if now mechanical source is taken out, the motor keeps on rotating with the speed ns, that is synchronous speed. Now there are different methods of starting synchronous motor. The first one is providing damper winding. Damper winding, here you can see they are situated this way, and the rotor pole shoe, here you can see the rotor field winding which are shown in the hashing part. This is the rotor pole N, and at the pole shoe there are damper windings placed around the rotor shoe. Now damper winding consists of copper bars placed in slots provided on the pole shoes of salient rotor poles. These copper bars are short circuited with the help of short circuiting ring on both the ends. This winding is similar to the squirrel cage winding. So at the starting, field winding is kept unexcited and motor is not loaded. Three-phase voltage is applied to stator winding, and the rotating flux produced links with the short-circuited damper winding and induces EMF in it as per the Faraday's first law of electromagnetic induction. So motor starts as a three-phase induction motor. When it acquires near to the synchronous speed, the DC excitation is switched on and the motor is pulled into synchronism and run as a synchronous motor. This motor is called as an induction start synchronous run motor. Now second method is the use of pony motor. Pony motor is a small induction motor which can be geared to synchronous motor. This induction motor drives the synchronous motor, and when the speed is nearly synchronous speed, the DC excitation is made on to the rotor and the motor pulls up the synchronism at the same time. The induction motor is switched off and may be disconnected, detaching its gearing. So this is basically the use of pony meter, where a small induction motor is geared with the synchronous motor and it is used to drive the synchronous motor, and once the speed is achieved around the synchronous speed or at the point of synchronous speed, the excitation is made on of the rotor and the motor pull into synchronism. Next method is exciter used as a DC motor. So here the exciter itself can be run as a DC motor. Supply may be separately available, and this will drive the synchronous motor up to synchronous speed, and the required synchronous speed is achieved, then the exciter is switched on and the rotor is pulled into synchronism. And the fourth method is DC generator as a load of synchronous motor can be run as DC motor. Now the load, here the DC generator is run as a DC motor to drive the rotor of the synchronous motor. When the rotor of the synchronous motor reaches synchronous speed, the exciter is switched on and the rotor is pulled into synchronism. Now the same synchronous motor drive this DC generator. So all the methods you can understand, there is some mechanism which run the motor and bring the motor into synchronism by any of the means, and once the motor reaches to the synchronous speed, the exciter is switched on and the rotor is pulled into synchronism. The applications of synchronous motor. The synchronous motors have many applications. The first, understand the polyphase synchronous motors applications. The first one is it is used as a power factor correction. Overexcited synchronous motor or the synchronous condenser having leading power factor. So it is widely used for improving the power factor. The second use is constant speed or the constant load drives. So most of the synchronous motors are used in driving DC generators, rubber mills, textile mills, pumps, ship propulsion and compressors. And the next use is voltage regulation. Because of inductive loads, the voltage at the end of long transmission lines varies greatly. Hence, as a voltage regulator, synchronous motor is used. And single phase fractional HP synchronous motor are widely used in clocks and stroboscopes. Now there are two types of curves in the synchronous motor. The one of which is V curve of the synchronous motor. It is the graph. You can see here in the diagram, it is a graph between the stator or the armature current versus the excitation current or field current. Here you can see the structure or the shape of the curve is V. So it is called as a V curve. It is between the stator or the armature current versus excitation current. V curves of synchronous motor show how the armature current varies with the field current or the exciting current when motor input is constant. Armature current is more for low values and high values of excitation, though it is lagging or low excitation and leading for high excitation. It has minimum value corresponding to certain excitation. The variation of armature current with the excitation is known as a V curve. Inverted V curve of synchronous motor. Now this is the graph of power factor with respect to excitation current or the field current. For the same input, armature current varies over a wide range and so causes the power factor to vary accordingly. Now overexcited motor runs with the leading power factor. Here you can see the overexcitation part with the power factor leading. Underexcited part is running with a lagging power factor. In between the middle point, the power factor is unity. The variation of the power factor with excitation is like a inverted V. So the graph is called inverted V. Minimum armature current corresponds to unity power factor. Hunting of synchronous motor. When suddenly mechanical load on the rotor shaft increases or decreases, then it causes rotor oscillations and rotor oscillates about its equilibrium point. Now it falls back or advances position corresponding to the mechanical load. Rotor oscillations are called hunting or surging of the motor. Now hunting is highly undesirable because if the rotor oscillation frequency becomes equal to the natural frequency of the rotor, mechanical resonance will occur. Amplitude of oscillation will increase to a very high value and there is a possibility that the rotor may fall out of synchronism. Now for reducing hunting effect, the damper windings are provided. The damper windings are copper bars provided on the rotor pole shoes and short circuited on both sides. So here in the diagram you can see the light load, there is a gap of alpha that is small and heavy load you can see alpha is larger. So due to this the rotor and stator there is a gap between them and rotor fall back and causes oscillations. The comparison between synchronous and induction motor. So some of the comparison points are here. Synchronous motor run at a constant speed at any load, but induction motor speed slightly decreases at a higher load. Synchronous motor can be operated at any desired power factor unity, leading or lagging by changing excitation. Induction motor runs at only lagging power factor. It is not self-starting synchronous motor, either damper winding is provided or it is run first by some means. Induction motors are self-starting. Synchronous motor changes in the applied voltage do not affect the torque. In induction motor, changes in applied voltage affect the torque. Synchronous motor requires DC excitation for rotor field winding, but there is no DC excitation required in induction motor. Construction is complicated, simple and robust construction. For same horsepower, motor is bulky for the synchronous motor, but comparatively the light in weight induction motors are used for the same HP. Cost is more for synchronous motor, cost is less for induction motor. High efficiency of synchronous motor, induction motor have low efficiency. And these synchronous motors are used for specific purposes like constant speed, power factor improvement, and voltage regulation. And induction motors are used in industries. Thank you everyone for watching my video. If you like this video, so please like a button and share and subscribe to my channel. Thank you everyone.